So the last kind of sample statistic that we're going to explore in any detail as it concerns their sampling distributions are sample variances. Now's a good time, I think, to talk about what statistics are in the language of probability. So we should go back to basics and think about what a random sample actually is. So a random sample, we understand to be data collected or a subset of a population and from which we collect data. So if we're talking about the language of probability, a random sample is actually a collection of random variables, and from each we get observations, so specific values which are lowercase are observations from this collection of random variables. And we assume, though this may be a flawed assumption in some certain cases, that each random variable is independently distributed. In other words, observing one outcome doesn't change the other outcomes. So then we are actually thinking about each random outcome as coming from a random variable, which then suggests that a statistic really, which we often denote with theta, is some measurement involving these x sub 1, x sub 2, x sub n, and every specific instance of that statistic, a mean, a median, a standard deviation, is just one random statistic drawn from this distribution of statistics. Maybe I'll use and so this is what we're doing when we're talking about the sampling distribution of a mean. So just in the context of a mean, for instance, right? So means, we have the sample mean statistic, and we get specific values for the sample mean depending on the random sample that we've drawn from the population. That is to say that statistics often are estimating parameters. So just as when we talked about in the very beginning of the class, we have a population from which we draw a sample. We hope that it's representative, and that's why it's important for us to never forget our sampling methods. And if a population has a parameter associated with it, like mean, like variance, like proportion, then we hope that the sample statistics associated with those are on target in some sense. So what do we mean by on target? So we're talking now about random variables being estimators. So these statistics are estimators of parameters. And our hope is that the expected value, so the expected value of that statistic, whatever it may be, we can call it theta, is going to be the parameter value. So population parameter. In the long run, if we take more and more observations from our statistic, the mean of those observations should be the population parameter we're looking for. And it's for this reason that we've defined the sample variance what it is. So recall that the sample variance given a sample data set is the sum of, from the first data value to the last, the square deviations, in other words, differences from the sample mean divided by the sample size minus 1. Why do we define it this way? Because we define sample variance as a random variable or estimator to be capital S squared, and that's the sum from k equals 1 to lowercase n of all of these random variables minus the sample mean random variable squared all over n minus 1. And our hope then is that the mean of this random variable is actually the parameter we hope to estimate, which is the population variance. So this right here, since we want this to be true, we have to divide by n minus 1, not by n. If we divided by n minus 1, if we divided by n instead, we'd actually be underestimating the population standard deviation. So there's a lot of symbols floating around here, but just remember that what we're saying is, if we want this to be a good estimate of this in the long run, then we have to define it the way that we did. So that's the explanation that you may have been waiting for a while. But then, though, the question remains, what is the sampling distribution of the sample variance? And the answer to that is actually, we need to introduce a new kind of sampling distribution. So, importantly though here, we need random samples of some size n from a normal distribution. Previously, it did not matter if we were taking from any kind of distribution whatsoever, as long as we had some sufficiently large size n. But here we absolutely need to be taking them from a normal distribution. Otherwise, we are out of luck. So when we have this, and if we have the sample standard deviation, sample variance is S squared, that's the random variable. And we have the population variance, not a random variable, it's a fixed value, right? Then we say this new random variable, W, being n minus 1 times S squared divided by sigma squared, has what we call a chi-square distribution with degrees of freedom n minus 1. So you want to read chi, so this symbol right here is chi, and we often say chi-square distribution, that's how we pronounce it, or we could write it that way as well. So what these distributions look like, we'll explore in a new video, and we'll practice working with them. But what's important to note here is that if we just modify the sample variance slightly by multiplying it by n minus 1 and dividing by the population variance, we have a random variable, which we historically call W, which has a chi-square distribution. And so we can find things out about sample variances that involve. So we can find probabilities and areas, critical values, all of the above.